A nice pleasure to welcome you to tonight's ISEP lecture. Dr. John Barrow was born in London in 1952. He graduated in mathematics from Durham University and received his PhD in astrophysics from Oxford, and held positions at Oxford and Berkeley before taking up a position at the University of Sussex in 1981. He is now a professor of astronomy and director of the Astronomy Center at the University of Sussex. You'll be interested to note that in July of 1999, Barrow will become a professor of mathematical sciences at Cambridge University and will be the director of the Millennium Mathematics Project, the purpose of which is to improve public appreciation of mathematics. Barrow has written 10 books which explore many of the wider historical, philosophical, and cultural ramifications of development in astronomy, physics, and mathematics. His books cut across traditional boundaries between the sciences and the arts to grapple with universal questions. Also, he has authored more than 260 papers in cosmology and astrophysics. But just for us Oregonians, and to show you his diversity, he was an accomplished half-miler and ran 150.2 at Edinburgh, Scotland in 1972. Barrow's talk tonight is based on his book, Impossibility, The Limits of Science and the Science of Limits. In it, Barrow lists some of the baffling limits of science, such as whether we can ever know the beginning and the end of the universe, whether it is finite or infinite, or whether the human mind can ever understand itself. Barrow concludes that limits are ubiquitous. Science exists only because there are limits to which nature permits. One reviewer recommended Barrow's book by saying it was fascinating, especially if you like dizzying, mind-bending ideas that will make your head swim. So tonight, let's bend our minds and please welcome Dr. John Barrow.
Well, I hope you won't believe too many of the things that the introducers have just told you about me. I have today already given several lectures here, and I've been introduced in different ways. On some occasions, I'm described as an astronomer, and on other occasions, I'm described as an astrophysicist. And people often ask me, what is the difference between an astronomer and an astrophysicist? And I always have to say that I don't really know, but when I come to America and go through immigration at the entering airport, and the immigration officer asks me what I do, if I tell him I'm an astronomer, he sends me straight on through. But if I say I'm an astrophysicist, he searches my luggage. Well, towards the end of each century, a strange malaise really seems to overtake the human race. They start to be infected by what we now call the Millennium Bug. They start to ask deep and searching questions about the meaning of things and whether everything's coming to an end, attempting to take stock of what's happened in the last century and look forward to what we might achieve in the next century. Some skeptics even think this is a good enough reason to cancel the last year of every century and just miss it out of the calendar. But one of the things I did some while ago was to look back and to see what people were thinking just a little over 100 years ago about what, if any, might be the limits of science. And the head of the German Academy, or the Prussian Academy, was a rather serious-minded man, none too popular with his colleagues at the time. He was a physiologist and a philosopher and a historian of science called Émile Dubois-Reymond. And he gave many lectures and wrote several articles about what he called the 7 riddles of the universe. These were 7 questions, the magnificent 7 as I call them here, which he regarded as unanswerable riddles of the universe that would not be solved in the coming century, and maybe not at all. And if you're the sort of person who's interested in reading popular science books or even doing science and following how the subject is developing at the frontiers, then you'll probably find many of his suggestions really rather interesting, because if you go down to Powell's or to Borders or other good bookstores around town, then you'll find that many popular science books are about these very same questions that Du Bois-Reymond raised over 100 years ago. The first three entries here, he regarded the problem of what is the origin of the forces of nature and what is the nature of matter itself as being completely unanswerable, because it would require us understanding the structure of nature down on infinitesimally small dimensions. The next problem of consciousness and the origin of our senses he regarded also as just impossibly complicated to deal with and beyond the reach of science. The third problem, likewise, that he regarded as unanswerable was that of free will. How would you come about with a scientific description of free will? And then his remaining four were problems that he didn't regard as intractable in quite the same way, but he reckoned that it would be many hundreds of years before we had any scientific answer to the issue of how did life originate and what is life? How did language develop and what is its structure? How does human reason operate in such an orderly fashion? How does it develop and issue from the mind? And finally, how do living organisms evolve and develop? How do they become complex, conscious, complicated living things? So you see, many of these questions have something of a resonance with our current considerations. Also, at this time, there was great interest, as the last problem indicates, in the whole problem of evolution and development and progress and change. And there was much debate as to how one might measure human progress. And one of the answers that was proposed, in an attempt to be less objective than people have been in the past, was to focus on our ability to manipulate and change the environment around us. And as that manipulative ability grew and extended, so some people thought we were progressing. Well, the issue of whether we are limited and what sort of limits we encounter in the scientific enterprise is very much tied to the place that we have in the grand scale of things within the universe. And in this picture, I've tried to map out something of that scale. Up on this vertical axis, I'm measuring the masses of things in the universe in grams. And it's logarithmic units, so this is 10 to the power 10, 10 followed by 10 zeros, 10 to the 20, 10 to the 30, 10 to the 40, and down here, 10 to the minus 10, 1 over 10 to the power 10. And along here, in the same sorts of units, in centimeters, are the sizes, the linear dimensions. So these rather human units place us right in the middle of the scale of nature as we go downstairs to the microworld of the bacterium, the DNA molecule, atoms and elementary particles, and conversely, if we go upstairs to the astronomical world of comets and asteroids and planets and stars and galaxies, and ultimately to the extent of the whole visible universe at 10 to the 27 centimeters, about 15 billion light years. So you can see that our own position in the scale of things means that if we really want to explore the structure of nature on the very smallest and the very largest scales, we're going to have to use artificial means in order to investigate the world of the very small and the astronomical world of the very large. Well, our own size is interesting for many reasons. And you recall there have been all sorts of attempts to write fantasies and fictional stories in which our size is changed in some way, or at least our size relative to the size of something else. Here's an old engraving of the 19th century from the famous Gulliver's Travels by Swift. And here's a rather more American style of inverted size, a rather unrealistic world of giant insects infesting our towns and cities. But at a more serious level, our size plays a crucial role in understanding what our capabilities are and what it is that we've been able to do. You see, human beings are just about the biggest living creature that goes around on two legs. And our size means that there are certain rather crucial things that we're able to do. In particular, we're able to use fire in a technological, useful way, and we're able to indulge in cooking food and changing our diet in that interesting and profitable way. You see, if you're an ant, you can't use fire because there is a smallest flame which can be sustained in air. You can't make a flame that's arbitrarily small. Our strength, which is determined by our size, is of a rather peculiarly interesting sort. We are strong enough so that we can wield rocks and tools, that we can split materials, we can break rocks, we can etch and break bonds in metals and other materials. So we're strong enough in primitive times to be able to make both useful tools and, in a more sinister way, also weapons which can be wielded in a way that is lethal to fellow members of our species. If we were very significantly smaller, we would not have the strength to break molecular bonds in stones and metallic materials. We would not be able to wield weapons with sufficient kinetic energy to do lethal damage. And so our technological development, our capabilities, owe a lot to our size. Also, our lifespan is directly linked to our size. Living creatures typically have a reproduction and a lifetime cycle which is directly proportional to their size. The smaller an insect or a small mammal, the shorter its lifespan tends to be. It's a much smaller evolutionary investment, and the number of offspring of those tiny creatures will be enormously larger than the number of offspring of very much larger creatures, where they're a much more serious and costly evolutionary investment, and they require more education, more nurture, more care in order to bring them to childbearing age. Well, if we try to break out of the bounds that are imposed upon us by our size and our position in the scale of things, we might take a leaf out of something that astronomers introduced into their subject about 40 years ago, when they were thinking about the problem of searching for extraterrestrial intelligences in the universe, something they're still also very much concerned with. And it was suggested by Andrei Kardashev, a Soviet astronomer, that one should try to classify the nature of advanced civilizations that might exist in the universe in terms of their technical capabilities. And he labeled civilizations in 2 or 3 classes according as to whether they were able to manipulate their local planetary environment, whether they could change and alter the characteristic of their local star, or whether they could even manipulate the dynamics and structure of entire galaxies. Well, suppose we steal this idea and use it as a guide to our thinking about how we might judge our own capabilities in manipulating our environment on large scales. We might say a Class 1 civilization has the capability of changing its planetary environment. This is something that we're able to do. We can alter the Earth's surface, we can mine materials, we can either directly or inadvertently alter the nature of our atmosphere by polluting it or making it rain in certain places, or by changing sea level, by introducing dikes and dams. So we certainly have the ability to change the surface geography and the atmospheric composition of our planet. And someone looking from outside would see energy changes and energy emission from our planet characteristic of those sorts of manipulations. The next most advanced behavior you might imagine would be a civilization that can change aspects of its planetary system. We can't quite do this. We might be able to do it if we wanted to. If a comet was to be discovered heading towards the Earth, then we could intercept it in the outer reaches of the solar system and deflect it onto another orbit so that it would miss the Earth. People think rather seriously about developing and perhaps one day having to use that capability. Becoming much more speculative, if we were even more advanced, we might be able to do things to nearby stars to alter their energy emission, to change the environment. A super advanced civilization might even be able to alter in some way orbits of stars within their own parent galaxy. And you could imagine extrapolating on to some ultimate capability to change the expansion of the universe and its structure. Well, no astronomer needs an excuse to show you a Hubble Space Telescope picture. So to illustrate some of these large-scale features of the universe, here's a beautiful picture from the Hubble Space Telescope of the Eagle Nebula. This is remarkable in that it's a picture of a nebula where stars are forming 7,000 light years away, and these great pillars of star-forming gas and dust and material, the colors are sulfur and oxygen and hydrogen. These are nearly a light year in height. And these are like cosmic factories where material is condensing into stars, making new types of stellar system, perhaps ultimately also new planets. While the world of the very large is rather difficult for us to manipulate, the world of the very small is something that we're much more interested in manipulating and using for our advantage. If we use the same type of classification going downstairs from class -1 to -2, -3, all the way down to minus omega, then one could say a class -1 civilization is able to manipulate solid objects of the same size as ourselves. We can break rocks, we can make bricks, we can build houses, we can create caves and dams, we can make structures from things of about our own size. But if we start looking on a much smaller scale, we recognize that we started to have the capability to manipulate much more microscopic structures. Very controversial at present, and part of a great international initiative amongst biologists, is the Human Genome Project, the ability to manipulate genetic information in particular ways. On a smaller scale still, we know how to create molecular structures to order, to make materials that have a particular molecular signature and handedness, a particular property. We know, in fact, even how to manipulate individual atoms, and this forms the basis of what's been called nanotechnology. This extraordinary picture, which looks as though it was taken at the rock concert here last night, is in fact a nanotechnological guitar. This guitar has a size that's 20 times smaller than the width of a single human hair. The strings on the guitar are just 100 atoms thick. And this has been constructed with a scanning microscope which is moving individual atoms around. Using the microscope, you can even strum the strings on the guitar. It produces sound, but not in our audially accessible frequency. It's very, very high frequency. So this is a glimpse of the sort of microscopic engineering that is now possible, and in the future will no doubt fill our world with microscopically small machines that may act perhaps as heart pacemakers or other type of ready medical supervisory devices implanted somewhere in our bodies or in our local environments. If we go to smaller scale still, we can envisage manipulating not just atoms, but even the nuclei at the center of atoms and the elementary particles of which they in turn are composed, and so on down to the most elementary constituents of space and time. In order to do that, we have to have some appreciation of the way in which nature works, what are the rules and regulations that govern it, what are the outcomes of those rules and regulations. And to appreciate what's involved, we have to understand two aspects of nature's makeup. First, there appear to be fundamental forces in nature. Just 4 of them are known at present: gravitation, electricity and magnetism, the so-called weak force that lies at the heart of radioactivity, and the so-called strong force that lies at the heart of nuclear reactions, that holds the nuclei of atoms together. Now, physicists are never very happy believing in a world in which there are 4 laws as opposed to 1 law. It would be rather like driving around town where there are 4 separate sets of traffic regulations in force at any one time. So what they're always looking for is a way of uniting these different legislations, these different forces, into a single underlying force, and then to see each of these separate low-energy forces that we experience in the world around us as separate manifestations of a single underlying force of nature. And to some extent, physicists have been very successful in that quest. They've shown that the weak and electromagnetic forces can indeed be joined together to form a single electroweak force. And such a theory makes definite predictions that new types of particles should exist in nature. And those predictions were confirmed in 1987 when those particles were discovered at CERN in Geneva. Physicists work very hard to complete the story, to join the strong force to create a threefold grand unified theory, and then finally a so-called theory of everything in which gravity is entwined in the story. And the favorite candidate for that is a so-called theory of superstrings. Now, what seems remarkable here is that all the complexity of the world around us is at root governed by just this very small number of fundamental forces, perhaps only one single force when you look at things in the right way. And yet, when we look at the world around us, we see an almost unlimited variety of complex and unusual states and structures and situations. And one of the secrets of the way our universe works is that although there are a very small number of symmetrical and simple laws governing the way the world works, the things that we see, the outcomes of those laws of nature, do not possess the same symmetries and simplicities as the laws themselves. When an outcome occurs to a law of nature, the underlying simplicity and symmetry of the law itself is broken. Suppose I balance this pointer vertically on my hand. If I were to let go of it, it becomes subject to the law of gravitation. Now, the law of gravitation is perfectly democratic. It doesn't prefer one direction over any other. So when you let go of the pointer, it doesn't always tend to fall in one particular direction. By giving it a little perturbation or putting it in a vacuum and letting quantum fluctuations do what they wish with it, it can fall in any direction. And when it does fall, it breaks the directional symmetry of the gravitational force. So in the outcome of that event, the symmetry of the law is broken. And this is how it can be that the universe can be governed by symmetrical laws, yet display all sorts of completely asymmetrical as well as symmetrical states. Well, what is the situation with regard to our understanding of the world of laws of nature and outcomes? What sort of problems are we faced with that we have to overcome? Well, on this picture, I've plotted, in a rather subjective way perhaps, some measure of our uncertainty of our knowledge of the basic laws or mathematical equations governing phenomena in nature. And along here, I've measured the complexity of the outcomes or the complexity of the phenomena. And this orange line here I've drawn in this way it sort of marks the region of the picture down here, where we really rather think we know what we're doing. We have a good grip on things. And up here, where we really don't have such a good grip on things. So there are situations where the complexity of what's being looked at is really not very great. Simple chemical reactions, for example. We have a good understanding of why you get a certain result of mixing two chemicals together. But if we move along here, we encounter situations of growing complexity. For example, the motions of all the bodies in the solar system. The weather. It's very hard to predict what the weather's going to be tomorrow unless you live in Palm Springs. But in most places, trying to predict the weather 2 or 3 days ahead is something that's extremely difficult to do. Not because we don't know the laws of nature that govern gases and fluids and weather, but because our knowledge of the weather here and now is incomplete. We only know the state of the weather at particular places over the land and the ocean. And the evolution of the weather system is extremely sensitive to its present state. And so a little bit of ignorance of its present state rapidly amplifies to become large ignorance. This is a situation that's become known as chaos or chaotic behavior. Another example of something that seems rather mundane is that of fluid turbulence. Turn on the faucet or the tap in your bath and you get a torrent of turbulent liquid. One of the great unsolved problems of physics is understanding in detail the behavior of that turbulent fluid. Technologically, extremely important. So on this picture you see these things along the bottom where we have difficulty understanding the complexity of the outcomes are nonetheless governed by laws of nature where our uncertainty is very small. We know the laws governing the motions and bodies in the solar system. We know the laws that govern fluids and weather systems and liquids. But the complexity of the phenomena is a limit and a barrier to our understanding of what's going on. If we look at other frontiers of physics, elementary particle physics, how to join together quantum theory and gravity, then we're dealing with phenomena that are really very simple. Elementary particles could not be simpler. Once you've seen one electron, you've seen them all. They're identical particles. And they do not make complex structures like turbulent fluids. So the simplicity of the phenomena they manifest, things like atoms and nuclei and so forth, the complexity is very low. But our uncertainty regarding the laws that govern them is considerable because it's so difficult to isolate those phenomena to create the environments in which their special properties are manifested. Up above the danger line, we run into all sorts of very flaky and complex situations where our ignorance due to complexity is compounded by our ignorance about the basic laws that govern how the systems change. When one comes to complicated living systems, ecological structures, the behavior of different human groups and societies, and their behavior when they start spending money or saving money. So predicting the future of the economy is much more difficult than predicting the weather, because when you predict the weather, you don't actually change the weather. But if I predict on the television what's going to happen to the economy next week, that actually changes the behavior of people and alters the economy in ways that I cannot take into account in my prediction. So these financial and social problems have a much higher degree of uncertainty and it's much more difficult to make meaningful predictions, as any consumer in a complicated society would tell you. All economists would deny this, of course. Well, what we learn from this type of picture is that it's perhaps useful to try to split up the problem of the limits of science into a number of particular types of limit that we could talk about one by one. And I want to stress in this talk that my attitude towards limits of science is that you shouldn't think of them as a rather negative attitude towards human capability, the idea of throwing one's hands up in the air and saying, I cannot imagine how we will ever be able to solve this problem. Surely this must be a limit to what we can do. I want to take a much more positive approach in that I believe that the pattern of the development of science in the 20th century has illustrated a profound fact about limits of science. That is, that when one develops a successful theory of some area of our universe, some aspect of science, perhaps it's a theory of elementary particles, a theory of gravitation, a theory of chemical reactions, a theory of information transfer, then there is a typical symmetry in what happens. The theory becomes more and more successful, people become more and more pleased with what it's doing, and gradually people start to predict that perhaps there is no limit to what this theory might be able to do within its sphere of influence. But then something unusual tends to happen, that what happens is not that the theory fails to explain something or fails to predict something, but the theory actually predicts that there is something that it cannot predict. It actually establishes that there are limits, self-imposed limits, on its capability. So in the case of relativity, we were shown internally by that theory that there is a cosmic speed limit, that you cannot send information faster than the speed of light. The theory of quantum mechanics, which successfully explained the properties of atoms and molecules, then showed us that there was a fundamental limitation on the accuracy with which we can measure states and situations in the universe on the microscale. In mathematics, we'll see later on in the talk, Girdle taught us that there are fundamental limits to what we can prove and disprove using the rules of mathematics. So this unusual pattern wherein a rather mature and successful theory turns out to be self-limiting. It tells us something about its own limitations. And it seems that this property of self-limitation is a consequence of a theory that attains a certain level of complexity and sophistication. Well, the type of limits that I want to just introduce to you with some interesting examples of how they may impact upon things that we would want to do, one can divide up into these four categories: cognitive and practical, and fundamental or intrinsic. These are the most interesting, and I'll spend most time telling you about some of those. And then finally, just a word about cosmological or astronomical limits. Well, what do I mean by cognitive limits? In some ways, this is the most obvious worry. The human mind did not develop with the purpose of doing scientific investigation. The human mind is something of a rag-bag collection of all sorts of different influences and biases and instincts and learned behaviors that millions of years ago began their evolutionary development with certain rather basic goals in view. And those goals were really to multiply and to survive. And there are certain attributes which help that survival process, and those attributes will therefore tend to be passed on to ancestors and to be inherited and to multiply within the population. Behavior patterns which do not aid reproduction and survival will therefore tend to die out more probably than those that do not. So we might worry, how can we be confident that the human mind is a reliable instrument for understanding black holes or galaxies or elementary particle physics? There seems no evolutionary reason, some might argue, why we should have the ability to understand those structures. The human mind is mainly primed for social interaction. It's rather good at hiding what it's really thinking and dealing with other people in complex, intuitive ways. on the average, human beings are not terribly good at doing mathematics. They're nowhere near as good at doing mathematics as they are at using language. Language is by far and away the most complex and sophisticated thing that human beings ever do. Our linguistic ability is phenomenally complex and very highly developed. We've all met plenty of people who are not very good perhaps at doing mathematics, who cannot play any musical instrument, but we have not usually met any able-bodied, healthy person who is not able to use language. And they can use it in an extraordinarily sophisticated way. So we might worry that there are perhaps innate conceptual limitations in our minds that might stop us doing science in every direction that we might want to do it. Well, one could counter to that. How might that not be the case? Well, perhaps you don't have to be programmed and primed to be able to understand black holes and Einstein's theory of gravitation in order to make progress in doing astronomy and physics. You see, maybe it's possible to understand things like black holes and galaxies by joining together lots of very, very simple concepts. Concepts like cause and effect, choosing one thing or the other. And by joining together many of these very simple concepts, we build up step by step a much more sophisticated conceptual ability which enables us to penetrate these more awkward and peculiar scientific problems. But there is an interesting speculative possibility one can introduce here with regard to the logical limitations of the workings of the brain. People like to tell us that the brain works as a rather complex and unusual type of computing system. It's not like the computers that sit on your desk in any way at all. It seems to program itself in sophisticated ways. And people who study artificial intelligence attempt to fabricate copies, as it were, of the human brain, like Marvin Minsky, have introduced rather interesting ideas that in some sense the brain is rather like a society, that there are competing voting influences within the brain, that if you do a certain thing repeatedly, that becomes reinforced in the neural networking of the brain, and if you stop doing something, then the networking will tend to become weaker, and eventually it will cease to work. Well, these great impossibility results that I mentioned just now about there being a cosmic speed limit, the Heisenberg uncertainty principle of quantum mechanics placing a limit on how it's possible to measure things accurately on the microscale, there is an analogous fundamental limitation that goes by the name of the arrow impossibility theorem in the subject of economics and politics. And the idea of the arrow theorem, for which Arrow received the Nobel Prize in 1972, and this year's Nobel Economics Prize to Sen went to someone else who played a role in this particular problem. And what Arrow's theorem shows is that under very reasonable conditions, there is no logically pleasant and consistent voting system. What do I mean by that? Here's the simplest example. Suppose we have 3 voters, 1, 2, and 3, and they have to exercise their choice regarding 3 options, A, B, and C. So next week when you go out to vote for your senator or whoever, you can apply this little logic. So voter number 1 prefers candidate A to B to C. Voter 2 prefers candidate B to C to A. And voter number 3 prefers C to A to B. Well, if we tot up the results, something very strange happens. A beats B here, B beats A here, but A beats B. So A beats B by 2 to 1 in the whole poll. B beats C, but C beats B here. So B beats C by 2 votes to 1. But does A beat C? No, A beats C here, but C beats A here and here. So C beats A by 2 votes to 1. So we say that the system is intransitive. So what's going on here is that when you have logically consistent single individual choices, they do not necessarily lead collectively to the same logical collective choice. So these preferences are all perfectly rational, but the collective choice does not possess the same rationality. And so if, like Minsky, you want to think of the human mind as a society in which there are voting preferences, and we all sort of know what it means to feel in two minds about doing something and trying to make up our mind in some way, we don't know how that splitting and choosing occurs. But if it occurs by some process rather like this, you see the workings of the mind become limited by theorems of this sort, which tell us that collective choices don't necessarily logically respect the individual preferences. Incidentally, the space program has voting computers. I don't know how many it uses these days, but when the space shuttle is launched, sometimes you hear that a computer has aborted the launch at the last moment. What happens is that several computers analyze all the information available for the launch system, and the computers vote as to whether the launch should occur. And the computers process information differently in different cases. And so you might well, with 3 computers, have a 2-to-1 vote to launch the shuttle. So in many complex technological areas, there is the potential for voting computer systems. Practical limits to scientific progress are rather obvious in certain respects. The lesson that we've learnt from elementary particle physics is all the deepest secrets of nature's laws are locked away at the very highest energies. Energies, our theories predict, which are many, many billions of times greater than the most energetic particle accelerator that we can build on Earth at present. We have no possibility of building such accelerators on Earth. Our only hope to probe those ultimate high energies where the secrets are hidden away is by astronomy. We know that in the past the universe was as hot and as dense as ever you like to contemplate. And perhaps one can use the astronomical relics and remnants and fossils from the beginning of the universe as a way of exploring what physics was like at the highest energies on the very smallest scales. Even if we have the mental ability to conceive of the ultimate theories of elementary particle physics, there is therefore no guarantee that our situation will allow us to test those theories experimentally. The universe is not constructed for our convenience. It is not necessarily the case that we should be able to manipulate materials on our planet and in our laboratories, which will allow us to test every scientific idea which we put forward. There are financial costs, there are costs in terms of energy and manpower that may divert these investigations into other more life-supporting areas of big science in the future. And we've seen in my earlier picture that the problems of chaotic unpredictability and complexity place limits on our ability to follow and predict the behavior of unusually complex systems. But next I'd like to look in more detail at what I regard as the most interesting and peculiar and fundamental limitations to our inquiry into the structure of the universe. And they concern 3 rather unusual concepts of intractability, undecidability, and uncomputability. And I want to show you a number of simple examples which bring home to you how it can be that you might have extremely simple situations which nonetheless are intractable in the sense that they require longer than the age of the universe to solve the problems that they pose. Probably everyone here has had a go at solving one of these so-called monkey puzzles. This is the poor man's Rubik cube, the plain analog of the Rubik cube, if you like. A typical monkey puzzle has 9 cards, square cards, on which there are 4 halves of different colored monkey shapes. And the problem is to organize the cards into a 3 by 3 cube in such a way that the tops and the tails of the monkeys of the same color are all matched up. And human beings are really rather good at doing this. It's difficult to analyze quite how they do it. But suppose you wanted to program a computer to do this. That is, to solve this problem algorithmically in a systematic fashion. Then for the case of 9 cards, the computer has to carry out a particular number of trials. It picks one card, and then it tries all the options, and it gets that one to fit, and then it takes the 3rd card and fits that, and so on and so on. And this requires 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 separate manipulations by the computer. So this is called 9 factorial. And it's an enormous number, more than 362,000 separate steps. If you were to make the puzzle just 1 dimension bigger, so have 36 cards, so the puzzle is still just 4 by 4, it could still fall out of your fortune cookie or your Christmas cracker, then if you set the computer to work on that, it would need to make 36 factorial steps. And this is a fantastically large number. It's got 41 digits in it, and if you computed using 1 million instructions per second, it would take the computer 11 billion years to search through all those steps. So this is what's meant by intractability, where one can have a problem that's rather simply posed, but in which the amount of time it takes to systematically find the solution is out of this world. Another example, sometimes called the Towers of Brahma or the Towers of Hanoi, depending on which culture you come from, that there is a legend that in Benares, in India, there's a temple, and at that temple there are 3 great discs set on the ground which have pillars growing out of them. And on top of this pillar, over here, pillar A, there are 64 discs of declining diameter placed one on top of the other. And the legend is that these 64 discs were placed in this pile when the gods created the universe. And the religious observance that's required of the priests at the temple is to carry out a particular operation with the discs. They have to move the discs one at a time from pillar A to B or to C, but in such a way that they never put a larger disc on top of a smaller disc. So they move the discs one at a time, so you might move this small one to here, and then the next one over to C, and then you might move this one back on top of here, and this one on top of it, and so on. So in a long sequence of moves, the name of the game is to move all the discs from pillar A to either B or to C, so they're stacked up in the same descending order of size. And the legend has it that when that process is completed, the universe will come to an end. Well, if you're fairly good at mathematics, with a bit of work, you can figure out how to do this. And there's a little algorithm, and you can work out that the quickest way in which you could move n disks from this pile, where n is any number you like, is in 2 to the power n minus 1 moves. So that's 2 multiplied by 2 n times. Now, if you have 64 disks, 2 to the power 64 minus 1 is a particularly huge number. If you were moving the disks at 1 per second, it would take you 1,000 billion years to move all the disks from one stack to the next. So this is another process. It's not like the factorial process of the last one. So it's a process where a number is raised to the power n. So again, it's a seemingly simple and mundane operation. If you were to set a computer to solve this problem, you would have expected it to be able to carry out these manipulations and moves on the screen almost instantaneously. But even if it could do it for 64 disks by carrying out 1 billion operations per second, just by changing the number of disks to 100 or 200, you could put the problem out of the reach of the most powerful computer on Earth by an enormous margin of time. There is another problem of this tractability sort, which illustrates the limits that are imposed upon us by complexity and computability requirements, and it's a famous problem called the traveling salesman problem. And I've just shown it here in a case where a salesman wants to visit, say, 6 cities, and he's supplied with the costs. These may be his travel costs or his costs in time in some way of making the trip between any pairs of cities. And the problem he's faced with is, what's the optimal way to go around all the cities, so you visit them once and once only, which minimizes the total cost? Well, you can see that it's not so obvious as this problem gets bigger quite how you go about thinking this through and working it out. In the case of 6 cities, the solution of the problem is shown here. This is the optimal path around the cities. Now, the problem of what is the algorithm, what is the computer algorithm which will systematically solve this problem, is still unknown. It's one of the great unsolved problems of computational optimality studies, that if you could find a foolproof and rapid algorithm which would solve these problems in any case for any number of cities, you'll be a very wealthy person. To illustrate a more practical example of it that's really very topical, here is a picture of the largest solved traveling salesman problem. And what it corresponds to is a problem in chip manufacture in the computer industry. So this is a blown-up picture of a chip, and the analog of the traveling salesman problem is that there is a huge number of points here that you want to wire by some robot device. And you want to find what's the optimal route, what's the quickest route for the robot to wire together all the points in the circuit board so that it perhaps uses the minimum amount of time or the minimum amount of material. And you can see this is an important thing to know. If you're making millions and millions of these circuit boards, if you can somehow halve the cost by clever use of mathematics, there's an enormous financial gain. So this particular example solved the problem for 3,038 sites. It's far and away the biggest traveling salesman problem that's ever been solved, and it required 18 months of computer time on the world's most powerful computer. So one gets some perspective here as to how one can be swamped by complexity in problems that sound straightforward and easy to pose. Here is a graph of what's really behind some of these problems. Here is the value of the number of pieces of monkey puzzle, the number of cities that one wants to visit, and so on, that I've been calling n. And if we have a problem where there are, say, just 5n possibilities for the computer to explore, then the number of things that it has to do and the time that it takes to do it grows really rather slowly as the problem gets bigger as n increases. But then more complicated problems are ones where the time you require grows as some power of n. The problems like the moving the disks in the temple, they grow faster than any power of the number n. They grow as 2 to the power n. And similarly, the monkey puzzle problem also grows more rapidly than any power of n. And you can see for values of n that are really quite modest, values of 100 or so, you end up setting yourself the number of operations that very soon becomes larger than the number of particles in the universe, or you require a computational time longer than the age of the universe. So there are limits to what one can do computationally, not because there are points of principle, but because the time constraints are so vast. In the modern world, cryptologists exploit this feature to develop codes which are unbreakable in practice. So although there may be a procedure for breaking a code, you can make sure that the computational process required to effect it would take such a staggeringly long time that you've got plenty of opportunity just to change your code before the other side could ever break it. And to give an example of the type of thing that you want to do, you're looking for a process that's extremely simple to operate in one direction. So this is like encoding a message, but virtually impossible to reverse and go back in the other direction. Mathematicians call such operations trapdoor functions. It's like falling through a trapdoor in the ceiling. It's very easy to fall through in one direction, but awfully hard to climb back through in the other. And the process that's been chosen to lie at the heart of most military and industrial codes is based on a very simple feature of numbers. And that is, if you take two prime numbers, that is, numbers that can only be divided by the number 1 and themselves, and multiply them together to produce a compound number, then that multiplication process is straightforward for any calculator to do. It'll do it in a split second. And that will correspond, in some complicated way, to the coding process. But suppose you want to go in the opposite direction. So someone gives you a compound number, or a number with maybe here like 160 digits in it, and you wanted to set a computer the problem of discovering if it had two factors. Then this is a problem which, in this case, for these two largest known prime factors of this 180-digit number here, took 100,000 hours of supercomputer time to solve. So after a few hours, you could quite well change your coding system. This would be a code that would be unbreakable in practice because of the enormous intractability of factorization. This problem of tractability and computability has rather striking analogues in some problems in molecular biology. One of the great unsolved problems in molecular biology is to understand how it is that proteins fold up to become complex three-dimensional structures. What happens in the protein folding problem in living beings is that proteins are linear sequences of amino acids strung out here rather like beads on a necklace. And what happens is that in a very short time, just a few seconds or so, this one-dimensional necklace will fold down to produce a fantastically complex three-dimensional structure whose exact shape and pattern will determine what the protein does in a biological situation. But nobody knows how it is that the linear chain here knows how to effect the three-dimensional pattern. If you look at this just mathematically, the process of several hundred or several thousand amino acids collapsing to form one of these three-dimensional proteins seems to be one of these intractable, uncomputable problems like the traveling salesman. And it would take hundreds of thousands of hours of supercomputer time to figure out what would be the state with the lowest energy and the optimal structure that it should fold to form. But yet all the time, nature carries out this folding process in just a few seconds. How on earth does it do it? How does it know how to find this optimal configuration? Is it perhaps that natural selection has chosen in some way those molecules which happen to have a very simple and easy way of effecting the folding? I think we don't know. So the problems of tractability and computability infest even these biochemical problems that lie at the heart of medical science. Well, let's move on and look at something more profound. What we've been looking at, we could think of as a little island sort of in the whole ocean of truth and reality. We've been thinking about that there is a little subset of problems that science deals with that we might call the practically computable problems. So these are like the things you run on your personal computer that the industrial world solves on large supercomputers. And these problems are practically computable. By that I mean one can do it in a sensible and finite amount of time. But we've just seen that there are other problems which, although they're computable in principle, like a large monkey puzzle or a traveling salesman problem with 1 million sites, in practice they're not really practically computable. They take vastly longer than the age of the universe to extract their solution. But in fact, there are even worse situations. Within this computable truth set, there are what I should have called here undecidable. Well, first of all, there are decidable truths around here. What I mean by that is that one can make a statement in the language of mathematics, and one can use the rules and regulations of mathematics to decide whether that statement is true or whether it's false. But surprisingly, there is another world beyond the world of decidable truths. In the early years of this century, Girdle showed that there are other mathematical truths which we cannot demonstrate to be true, or false statements that we cannot demonstrate to be false by systematic mathematical reasoning. And the last bit of the talk, I want to try and tell you something about how that rather profound idea developed and how one could prove such a result, and then to ask whether it has any implications for science. Well, Girdle's famous theorem from the 1930s in ordinary language is really saying that there are mathematical formulas which cannot be shown to be either true or false by using the rules of arithmetic and mathematics. And the way you demonstrate such a theorem is by setting up a correspondence between mathematics and mathematical formulae and statements about mathematics. And in this way, you can then exploit some of the strange paradoxical self-reference problems that infest the world of statements, paradoxes like this statement is false. And you can find their equivalent within the formulae of mathematics. Now, to understand how Girdle arrived at this, many people regard as the most profound and deep result in mathematics and in logic, one just needs to understand one simple aspect about numbers. And that is the concept of a prime number that I introduced just now. A prime number is a number that has no divisors. So 3 is a prime number, 6 is not, because it's divisible by 2 and 3. Now, it's a profound property of any number that you can split it up into its divisors in one and only one way. So you can keep breaking down the divisors till you just get to the prime numbers. So 51 is 3 times 17. These are both prime numbers. 54 looks like 2 times 27, which is 2 times 3 times 9, which is 2 times 3 times 3. It's 2 times 3 cubed. So this is the basic prime decomposition of the number 54. And it's unique. There's no other way to do it. If one looks at a much bigger number, like 9,000, then the decomposition is 2 cubed times 3 squared times 5 cubed. Now what Girdle did was to give every number a label, and that label that we now call the Girdle number is just the listing of the powers to which each prime in this product is raised. So this Girdle number is 323. If there was no entry in 3 here, if it was 3 to the power 0, you would enter 0. If you take a huge number, like 24 million, it looks like 2 to the 6th times 3 to the 5th times 5 to the 6th, its Girdle number is 656. Now, because this prime decomposition can be done in one and only one way, we have now an essentially remarkable feature. Every number has one and only one Girdle number. And every number is the Girdle number of one and only one other number. So there is a one-to-one unique correspondence between numbers and Girdle numbers. And what Girdle did was to introduce a sort of code. So every number that was appearing in a Girdle number, he gave some meaning in terms of arithmetic symbols. So the number 6, for example, corresponded to 0. 5 corresponded to equals. 6 is again 0. Other numbers like 1 and 2 and 3 and 7 had other meanings, greater than or less than, and so on. So each Girdle number then defines a statement of mathematics. 656 gives a trivially simple statement. It's just the statement that 0 equals 0. So by this simple device, Girdle set up a correspondence between mathematics and statements about mathematics. So any number of arithmetic had associated with it a Girdle number which corresponded to a statement about arithmetic. And then all he did, in effect, was to consider the following sentence. The theorem having Girdle number x is undecidable. Undecidable means that you can't show it to be true or false. And then he simply worked out the Girdle number of this sentence and substituted it in for the symbol x here. And the result then was a statement which proved its own unprovability. So this is a rather cute and interesting demonstration. It has all sorts of curious spin-offs for science that are much more easy to visualize. So what it's telling you is that mathematical truth is something that's much larger than provability. So there exist mathematical truths which you can't get at using the rules and regulations of arithmetic. To give a concrete example of this, in recent years it's been shown that the result is equivalent to a statement about randomness. Suppose I have two symbols, 0 and 1, and I write a never-ending sequence of them in a line, and I ask whether this sequence is random or not. Well, by random, what mathematicians mean is that there's no way of replacing this sequence by some little rule or formula or program that's shorter than the listing of the sequence itself. If the sequence was ordered, if it was all zeros, for example, you could replace the sequence by a little rule, print 0. And so you can compress the information in the sequence into something that's shorter than the listing of the sequence itself. Now, it turns out that you can never show that a sequence cannot be compressed. You can never prove that a sequence is random in this way. And the reason is, precisely because of Girdle's theorem, that undecidable truth of mathematics, which Girdle tells you must exist, might be the very rule and theorem that you require to spot the pattern in this sequence. In recent years, people have shown that this type of undecidability also infests other sort of familiar problems of mechanics and physics. If one has a system that's governed by equations, which can change a system in all sorts of different ways, the type of question that mathematicians and physicists are often interested in answering is a particular solution of the system stable? And a stable solution is rather like having sort of hills and valleys in this way. The stable solutions are the ones that sit down here in the valleys. The unstable ones sit at the top of the hill. If you give them a little displacement, they'll move off and go somewhere else. If you displace these slightly, they'll wobble around but eventually come back to rest where they started from. And it turns out that in general, the question of whether you can decide from the most general possible system of laws and equations governing change whether a given solution is stable or not is undecidable in the Girdle sense. Well, many people have speculated that somehow Girdle's theorem has some ultimate significance for our hopes of understanding the structure of the universe and our quest for a theory of everything. And many people will say rather quickly that obviously you could never understand all the laws of nature or derive some theory of everything because of Girdle's theorem. Physics is based on maths, and maths does not allow you to discover all mathematical truths, so perhaps we won't be able to understand all the mathematical structure of the universe either. Well, it's important to look at the fine print of Girdle's theorem, just like any insurance policy, to see whether this is really the case. And what you see is really rather interesting and intriguing. What Girdle's theorem says in detail is that if a mathematical system has three properties, if it's finite, so it has a finite number of rules and axioms and a finite number of entities and ingredients that you move around, things like lines and points and numbers. So mathematics jargon for this is that it's finitely specified. In fact, one doesn't have to even be finite. One just has to have a rule for generating the constituents so that it could be listed. So it could be an infinite number of pieces, but so long as you can write a little program that will list them all, that's good enough. The second assumption is that the mathematical system has to be big enough and complicated enough to include arithmetic. That sounds strange. What could that mean? For example, if you take geometry, subject Euclid invented in a sense in which one studies at school or you used to study, Euclidean geometry is a much smaller logical system than arithmetic, and Girdle's theorem does not apply to it. And the third requirement you need is that the system be logically consistent. That is, it does not allow you to prove that 0 equals 1, which would be rather embarrassing. Then if these things are true, then Girdle's theorem conclusion results, there exist statements in the language of this system, arithmetical formula, which you can neither show to be true nor false using the rules of reasoning of the system. And so one might ask, are there any implications of this for physics? Well, how could you evade the conclusions? There are various ways you could think of doing it. Perhaps physics does not have a finite number of axioms and rules. Perhaps there's a bottomless, infinite number of principles governing the structure of the physical universe, in which case this would not apply. If perhaps physics doesn't use the whole of mathematics and arithmetic, then it would escape these conclusions. To give a trivial example, suppose instead of having the whole of arithmetic, one just looked at the truths that you could prove from the first 9 numbers, the numbers 1 to 9. Then Girdle's theorem doesn't apply, and the set of all mathematical formulae just involving those first 9 numbers doesn't contain undecidable statements. But what I have in mind is something a little different. Although we use arithmetic and much more complicated mathematics in doing physics and science, maybe we only do that because it's awfully convenient. And we could get away, if only we knew how to do it, with a much smaller logical system. Perhaps something that was just like geometry or non-Euclidean geometry, both of which are not incomplete in this sense. So what one is saying is that perhaps science and physics might make use of only the decidable part of mathematics rather than all of it. But the real problem is, if one was doing physics and one did indeed encounter some statement that experiment led you to hypothesize was a law or a principle of nature, and you found that you really could not show whether this was true or false from the underlying assumptions and laws of physics that you had adopted, what would you do? You probably wouldn't throw up your hands and say, the situation is undecidable. You would just add that principle as a new axiom to your system. You can always do that. So if you pick an undecidable statement, you can add it to the system. That doesn't make the system decidable. There will be new undecidable statements. But physicists would just keep enlarging their system by adding any undecidable statement as a new axiom. The problem they then face is being able to decide in a finite amount of time whether a statement really is separate from the other axioms, whether you can add it in this way to the system. Well, so Girdles theorem is really rather peculiar. It shows us that if you have a logical system that's complicated enough, and by complicated enough here we mean complicated enough to include arithmetic, then it's necessarily incomplete and limited in its ability to determine whether things are true or false. So when one has logical structures that become complicated enough to give rise to living systems like ourselves, they necessarily have this incompleteness that separates what you can prove from what can be true. Well, finally, let me say something about cosmology, where limits enter the problem with a real vengeance. Cosmology is the study of the universe on the largest scales. And the most remarkable feature that we've discovered about the universe is the fact that it doesn't stand still. The universe is in a state of expansion. The distant clusters of galaxies are moving away from one another with speeds that increase with their separation. And there are two sorts of expanding universe one can contemplate: a universe that keeps on expanding forever, and one that will one day reverse its expansion into contraction. And in between there's a sort of British compromise universe, as I call it, which just manages to separate the two alternatives and keeps on expanding forever. And cosmologists work very hard to try and decide on which side of this critical divide we lie, and to answer questions like, is the universe finite, as in this case, or is it infinite? Did it have a beginning? Will it have an end? What is the global structure of the universe on the very largest scales? And so on and so forth. And there are obviously practical problems here in answering those questions. But there is a deep point of principle in cosmology that makes many of the ultimate questions about the universe that we would like to answer fundamentally unanswerable. And the point of principle is that we have to distinguish between what we might call the universe, that is, everything there is, and the visible universe, that portion of it that we can see. What do I mean by that? Well, if we sit ourselves here at this point and we ask, how much of the universe can we see with perfect instruments? Well, the universe has been expanding for some finite amount of time from its apparent beginning. That amount of time is somewhere around 13 to 15 billion years by our present estimate. Now, during that period of time, light has had the opportunity to travel at most about 15 billion light years. And so that marks a horizon for us in the universe. There certainly is more universe, we believe, beyond the horizon 15 billion light years away, but there has not been enough time for light and radiation to reach us from any further distance away. So the whole of astronomy and science is really the study of the structure of this finite, visible universe within our horizon. Although popular books and articles and magazines like to make confident statements about the universe, telling us that we will be able to show perhaps that the universe is finite or open or closed, really we can never do anything of the sort. All we can ever hope to do is determine something about the behavior of this finite, visible part of the universe. We might be able to decide whether it's likely or not that this had an origin in some event of extraordinarily high density that we might call the beginning of the universe. But it's not really the beginning of everything there is. We can never answer a question of the sort, did the universe have an origin? Or do we expect the universe to have an end? Because the information to answer that question is not available to us. We're limited in what we can discern about the structure of the universe by the finiteness of the speed of light. The finiteness of the speed of light at about 186,000 miles per second is what prevents us obtaining information about the whole global structure of the universe. Now, until rather recently, some philosophers and many astronomers used to take an attitude of saying, well, there really is no reason to believe that the universe is very different beyond our horizon to what it is inside. So it's a perfectly reasonable expectation to think that everything we conclude about our visible universe can be extrapolated about the great beyond that extends past our horizon. However, in the last 10 to 15 years, cosmologists have developed a new theory of what goes on in the very early stages of the expanding universe that goes by the name of the inflationary universe. Now, the inflationary universe is just a very simple nuance on the picture of the expanding universe that has it accelerate for a brief period early on. And one of the consequences of that acceleration process is that it can occur slightly differently in different places in the universe, with a result that is dramatically different from place to place. And so the inflationary picture of the universe, for the first time, leads us to expect that on the largest scales, beyond our horizon, the universe will be radically different in its structure, in its density, in the rate at which it expands, even in the number of dimensions of space and the strength and number of the fundamental forces of nature that exist there. And for the first time, there is positive reason to expect the world to be different beyond our horizon to what it is inside it. So here, the simple limitation imposed by the finiteness of the speed of light places a fundamental limit on our ability to answer those great and deep cosmological questions about the whole structure of the universe, its beginning, its end, whether it's finite or whether it's infinite. These are questions that we cannot therefore answer. Well, in conclusion, what have we seen? I hope that in this little talk I've shown you something about the idea of impossibility and the limits of science that is not entirely obvious. That the limits of science is not all a negative thing about not being able to do things because we can't imagine how to do them, but the fact that our most successful theories of physics and mathematics actually predict that they are self-limited, that there are computations which cannot be carried out in particular finite times, that there are statements and truths of mathematics which cannot be shown to be either true or false. And I hope that you therefore see that impossibility is something that really amounts to more than meets the eye. Its role is not just negative, and ultimately I think that what we learn about the limits of science through the structure of fundamental theories will come to characterize the nature of the universe perhaps just as sharply just as profoundly and just as deeply as the catalogue of the things that we can know. Thank you.
One thing we'd like to do is prevent the exodus here. So for those of you who, we are in a fascist mode at this point, and we don't want you to leave, so you have to stay around because we want to develop this part. And then those of you, if you have to leave, fine, but hang out, fascist mode, and then when the anarchy starts, those of you who get upset by that stuff can take off. Professor Art Kahn, again, is going to do our fascist portion here. Dr. Kahn is a cognitive psychologist and president of Kwamba Educational Multimedia, which develops video and internet training tools on a national and international basis. He and his wife, Dr. Wendy Kahn, also run Kudo Foundation, a nonprofit educational organization that sponsors educational safaris to Africa. If any of you want to go to Africa with Art and Wendy, there's a little thing, I think it's right inside the front cover of your deal, a little ad that I stuck in there for them. So at that, I will turn it over to them. What we'll do here is, if you have a question you want to write down, the ushers will go up and down, run them back to me. So go about 15 minutes this mode, then we'll move into the cards, and then we'll go into the anarchy mode with the microphones.
Thank you, Terry. I've never been introduced as a fascist before, so I appreciate that, I think. The goal here is actually not fascism, but instead to try to find an opportunity to humanize this portion of the seminars, and so that you can perhaps get a better idea. And my job is to try to represent the kinds of questions that I hope you might want to ask as well, to get to know our speakers better, and to ask the kind of collective questions to bring things together. And afterward, of course, there will also be cards and your opportunity to talk at one of the microphones that are situated here in the auditorium. John, I guess the place I'd like to start, and with our little visual display up there, as I was listening to the talk, I was troubled by your use of the word impossibility. And perhaps it's the American culture which says we can do anything. And when I hear the word in the book, it's called Impossibility, the Limits of Science and the Science of Limits. I guess so much of what I was hearing was impracticability, intractable, difficult. Well, many things were difficult only 20 years ago, and certainly 100 years ago, all of these things seemed impossible. And I guess what I would like to do is to ask you, are what we're talking about here are things that are simply difficult and we can't get at them, or are they definitionally impossible?
Well, there's a combination of the two. So we can see that what Girdles Theorem is telling us is that there are statements and truths in mathematics or in its applications to science which it is impossible for us to decide being true or false one way or the other. But then there are also other activities, other problems that we might want to solve that are intractable in the sense that they require enormous amounts of time. I mean, amounts of time which are longer than the age of the universe. So for all practical purposes, they will be out of our reach to solve. So there's a mixture of the two. If we're practically inclined, we're worried about problems which we cannot solve in astronomical periods of time, just as much as we're worried about problems which cannot be solved in principle.
But wouldn't you agree that prior to the existence of supercomputers, that factoring a 64-digit number would have seemed to be would have required more time than exists in the universe, but now that we have new tools available to us, we can solve these problems? Isn't it simply a matter of time before we come up with new tools?
Well, unfortunately, the time that you require to do the factorization increases so staggeringly with just making the numbers a little bit bigger that it's always very easy to keep the problem way, way out of reach of your most powerful computer. The only way around it may be, one day somebody might find some very profound and new back-of-the-envelope way to determine whether large numbers have prime factors. If someone were to do that tomorrow, it would cause a world catastrophe, because suddenly all high-level secret codes will become unsafe.
And then you would agree it's possible that that could happen?
Well, one's not sure. I mean, the factoring of primes is not the only intractable type of problem, but it's a very topical one because it does lie at the basis of coding. Nobody knows or has any inkling of mathematical developments in that direction. We don't know, for example, how to predict what the next prime would be. We know that there are an infinite number of primes, that there is no largest prime. Euclid himself proved this. And it's a matter of great interest and competitiveness to actually try and find the largest prime. And if you find the largest prime, it's extremely valuable commercially because it can be used for these coding purposes. I gather in the US there was something of a mini scandal a month or so ago. One of the things that amateur mathematicians who hunt for primes do is that they try to gather up like-minded people on the internet, and there are certain sorts of number that you can search systematically to discover if these numbers in this set are prime. And you just do it by chasing all the divisors on the computer. It takes, tens of thousands of hours of computer time. But if you can get tens of thousands of your buddies to use their computers as well, you can cut down the time for the whole operation. Now, the trouble was that one of the keen amateurs who wanted to join this little game was a manager at I think it was Pacific Telephone Company. And he decided in what he thought was going to be low activity time to actually use one of the company's principal computers, which was in charge of directory inquiries and routing, to run one of these problems. He thought it was going to have a minimal effect on the running of the system, but its effect was to change the whole response time to directory inquiries from callers from 2 or 3 seconds to about a minute. Well, he was appearing in court, I gather, a few weeks ago, had been fired and sued by the company because of this misdemeanor. So you can be a little too enthusiastic about it.
As we explore this, the concept of impossibility, we have an Escher, and obviously a two-dimensional representation of a three-dimensional space. Is that impossible? Could something like that, does that fit your definition of the impossibility?
Well, it's possible in some sense. People have built, curiously, there are fabulous three-dimensional models of these things, which, when you look at them in perspective, they look as though they really exist in 3 dimensions, but when you walk around them, they're weirdly distorted and just rely on tricks of superposition. But I think the interesting question that pictures like this raise is that we can see in all sorts of areas of human inquiry, the search for paradox is something that's deeply attractive and often very instructive. So impossible figures in art like this, in other forms of modern art, the play of a Lewis Carroll with logical paradoxes, even logical paradoxes deduced by logicians like Bertrand Russell or Whitehead. These all had very stimulating effects on the development of logic, just as these visual images have very stimulating effects upon our appreciation of space and geometry. Escher made discoveries intuitively about profound properties of mathematical spaces. In fact, many of these ideas for these sorts of figures were given to him by Roger Penrose and his father Lionel Penrose, who was a psychologist interested in impossible figures. That is, figures that it's impossible to fabricate in 3-dimensional space, even though you can represent them as 2-dimensional projections. So the impossible in the sense of the logically paradoxical or the visually paradoxical, or even paradoxes in sound, are very stimulating and have played a key role in the furtherance of many intellectual developments in this century and the last century.
Now, I'll present you with a language-based problem and ask you to, looking at this, does this represent impossibility?
Yeah, I mean, there's a whole host of statements like this that used to cause mathematicians and logicians and people in the street problems in the early years of this century. People became very worried about logic and about mathematics because they thought, well, if you can create a paradox of this sort, the more famous one was the Barb of Paradox, that in a town there's a barber who shaves all those people who do not shave themselves. Then who shaves the barber? We assume the barber is neither a woman nor has a beard. Okay, so if you follow through the definition, the barber shaves everyone who doesn't shave themselves. If he shaves himself, then he doesn't. If he doesn't shave himself, then he does. And this rang alarm bells amongst logicians in the end of the last century, because if you could create a paradox, a logical paradox like this, in such a simple way, how do you know that there might not be other paradoxes like that at the heart of arithmetic, so that when you do your tax return, that you get a sort of illogical consequence in this way? And people started to have deep worries about the logic at the heart of mathematics and arithmetic. But the way these things were unraveled in the end is that one has to very clearly distinguish between statements of mathematics and statements about mathematics. And statements like this one create their paradoxes by mixing together two categories of things. So a statement about something and a statement of something. And Tarski showed that because of this, there are always systems of logic and reasoning, and then above them there is another structure, which is the set of statements about that system of logic and reasoning. And then above this there's yet another structure, which are statements about that metastructure of statements about the first one. And one simple consequence of this is that there's no such thing as absolute truth. You can talk about truth within this system of reasoning, but if you move upstairs to the world of statements about the system, then truth is something different in that system. If you want to talk about that system using another language, then truth becomes something different. And there's a never-ending hierarchy, therefore, of truths, each which correspond to the statements within their own frame of reference. But there isn't a sort of absolute truth which governs all possible statements, like this one that sort of mix one category with another.
Last season, many of us had the pleasure of listening to David Chalmers talk about concepts of consciousness. And David argued that the concepts, when taken to their logical extreme, might require a whole new fundamental primordial element of the universe, and that consciousness potentially consists of a unique primordial element, or it is manifested somehow in complex structures. What can we ask your general reaction to the concept of consciousness and what it might mean in our physical universe?
Well, I've no idea what it is, but nor does anyone else, so I don't feel too bad about that. But I tend to take a sort of minimalist view in regarding it simply as something that emerges, that occurs when a particular level of complexity is achieved in a system. So I don't think there's any reason to believe that consciousness is some sort of cosmic influence that we just happen to tap into locally. I think there's no reason to believe that at all. But what we've seen from studies of the structure of the brain is that the brain is a network that's not like any computer that we've seen before, It's vastly more complicated, and it's really very hard to generalize that the structures of one brain to the next brain have very different, significant differences in the way they do things and how they use the neural networking that's available. So consciousness is, I think, the great scientific problem that will be addressed in the next millennium, in the next century. And again, it's a problem of tractability. One is never, as Mr. Dubois-Reymond recognized 100 years ago, one is never going to be able to sort of pin down the structure of the brain in such a way that you can see what happens when you're given a stimulus and follow the firing of every single neuron and say, oh, what's going to happen here is that this sequence of 1 billion neurons is going to fire one after the other, and that will give you a feeling of feeling happy. You know, there's not going to be any such explanation. The number of pathways, the number of possible responses, and the structure is just vastly more complicated and requires vastly more time to analyze than any computational structure that we have the potential to produce. So even if we could make an artificial intelligence, as it were, we would have a very difficult problem of deciding whether we would think it to be conscious or not. And if it was, of course, it might start to behave in rather strange and unpredictable ways, just like you and I. I mean, after all, I don't know that you're conscious. I mean, you tell me you are. And I believe you are, but only because, you know, you seem to roughly behave in similar ways to the way I do in certain circumstances. But we don't actually know that anybody else quite feels like we do inside. We just take it on trust. And so we would never know that our robot or our complex computer actually felt conscious in the way that we feel conscious.
I wonder if you could tell us, I had the pleasure of learning a little bit about your new appointment at Cambridge. I wonder if you could tell us a little bit about the kinds of research and the other opportunities that you'll be undertaking at Cambridge. Thanks.
Well, my own area of research interest is cosmology, primarily, all aspects of cosmology, the study of the very earliest stages of the universe, where one has to use elementary particle physics to make sense of the high-energy environment that the universe would have experienced in its first moments. One of the interesting things about that study is that one is trying to understand why the universe is as it is today, but conversely, one is hoping that by doing astronomy, one can learn something about high-energy physics. Those high-energy physics theories that we're never going to be able to test in accelerators because they require such high energies have exotic consequences for the early history of the universe. And if, for example, your favorite theory leads to the conclusion that galaxies and stars cannot exist, then you can rule that theory out fairly safely. And so in this way, without spending billions of your dollars and billions of my pounds on building huge accelerators, we can test high-energy physics theories using astronomical deductions and observations. So this is one of my particular interests, the problem of how galaxies form, why the universe has the shape that it does, the characteristics and structure that it does.
And a little bit about the other half of your responsibility at Cambridge.
Well, the University of Cambridge has decided to invent a new activity, a new project focused on the mathematics, the applied and pure mathematics departments, in which myself and Stephen Hawking and Neil Turok are based. And the idea is to really rather actively promote the public understanding of mathematics and its applications to science and all sorts of other more familiar problems, and to direct that in ways that make use of new technology in effective and inexpensive ways. So on the one hand, we might be hoping to enable school pupils to tap into information that we would be supplying over the internet, also offering courses to them and to their teachers to make optimal use of these facilities, to run courses for educators and teachers to bring them up to speed on new developments in mathematics and science, to tell them what's happening at the frontiers. so that they can infuse their pupils in new ways, to show them what mathematicians do and why the subject is exciting, how it applies to fundamental physics and to even more basic aspects of modern life, the financial world, the evaluation of risk and chance in society, even how you won't win the lottery if you buy lots of tickets. Also to try to display mathematics in ways that are more enticing and illuminating than traditional means of teaching. That instead of displaying mathematics as some great Platonic set of structures that you're either genius enough to appreciate or not, but to show how mathematics is all around us. Mathematics is really nothing more than the study of all possible patterns. Some of those patterns are in lines and sequences of numbers, but others are in mosaics, they're patterns in time, they're designs in carpets and friezes, they're patterns of markings on the backs of animals. So one can develop mathematics from some of the dramatic things around us in the world. Mathematics enables us to understand why the leopard has spots, why the tiger has stripes. It enables us to understand what is acceptable risk and chance. It enables us to understand why the heavenly bodies move in the way that they do. We can understand things like chaos and complexity. We can understand mechanics perhaps in a more exciting and appealing way by looking at what goes on in the world of sports, by looking at what the high jumper is doing when he uses the Fosbury flop. Why does the high jumper do that? Why not just hop over using the scissors style? What sort of information can you learn about running at high speed when there's wind assistance? What about throwing baseballs or hitting cricket balls? What can you learn about mathematics and mechanics by focusing on what goes on in the world of sports? So in this way, the subject is made rather more appealing than by just talking about massive objects moving from A to B under certain rather boring circumstances. So I think there's a great deal of scope to develop the appreciation of mathematics as well as the understanding of mathematics by these means. We tend as scientists always to treat a subject like mathematics in such a way that we believe that everybody is going to become a mathematician. And all the things that we tell high schoolers or adults about mathematics is formalized in a way that's going to help them pass examinations or become mathematicians. Now, we don't do that when we talk to people about music or about art. We don't have a policy in telling people about music that imagines everybody's going to become a musician. So it's important to have an appreciation of something like music or literature that doesn't imagine you're going to become a professional writer or a musician. And so with something like mathematics and with science, on the one hand, there's a place for systematic education for people who are going to become mathematicians or scientists. But it's also possible to teach and develop the appreciation of science and mathematics for people who are not going to be mathematicians, but who need to know something about what that subject's about, what it can teach us about the world, what we can learn about the world that we wouldn't otherwise know about it if we didn't have some appreciation of the structure of numbers and patterns that mathematics develops.
Some of us will recall, perhaps 2 years ago, Robert Ballard gave an amazing talk. And one of the things I remember from his presentation was his passion for teaching our young people, and said, I need young people to understand that my science is a contact sport. And it's exciting to see some of our top people being inspired to help our children become interested in science. Let me ask, in the introduction, Maynard mentioned that you had a bit of a history in running. I know you're a terribly modest fellow. He was actually incredibly successful. I think you beat an Olympic champion at one point, isn't that right?
Yes.
I hope that was informative.
Several, in fact, yeah.
You attempted at one point to write a book about sports. Is that on the horizon?
Well, again, a study of a sort of scientific look at sports is really rather fascinating. I mean, I wrote an article last year on the occasion of the World Athletics Championships, which was an attempt to find out really who was the fastest human. And it's interesting that it's not the world record holder, because when you run in a sprint event, there's a certain allowable wind assistance that validates the performance for record purposes. You're allowed to have a wind that blows behind you at 2 meters per second, but when it goes above that, it's wind assisted and it's not valid. But suppose someone sets a world record when the wind speed is 1.9 meters per second, and then someone comes along with the wind even blowing in the opposite direction and runs just 1/100th of a second slower. Clearly the second performance is superior. Now, with a bit of knowledge of what is the effect of wind resistance on motion, you can produce some formulae which allow you to recalculate what every sprinting performance would be if there were no wind. And you turn out actually completely rewriting the record books. Mr. Carl Lewis finds he's not even in the top 20 in the world.
Really?
Yeah.
May you share some of the questions that have come from our audience? Judy, thank you, Judy, asks, are the limits of science truly changing, or is it merely our knowledge that is expanding, making it appear that, quote, new things are being created? Is what exists today the same that will exist millions of years from now?
That's an interesting question, that limitations on what one can know in the universe do not necessarily mean there are barriers which you can't cross. I mean, imagine that all the facts that we wanted to know were spread out in front of us in an infinite, never-ending sequence. And the scientific process was such that we only ever picked up every other one of those facts. Then we would still find an infinite number of them, and we would never meet any barrier. We would keep on discovering new things forever, but we would have missed out half of the things in the list. So some sorts of limitation can be of this selective sort, that our search is clearly limited in certain ways. You know, we don't have the ability to see things that are infinitely small or to see things that are infinitely large. We cannot discern certain sorts of complexity. So I think the sorts of limits that we can envisage encountering are of this selective sort. And maybe in 100 years' time, we will have discovered new sorts of limit. If we imagine the situation 100 years ago looking forward, you might say, well, there were all sorts of things that we imagined that we wouldn't be able to discover or do, which we have been able to do. And that's quite true, but what has also happened is that we've discovered these fundamental limits that are springing up in different areas of science, and we've discovered these as well as the solutions to other problems. So I think it's just as likely we will discover other more fundamental limits. After all, there's no reason why the universe should be constructed, you know, for our investigative convenience.
Glenn wants to know, how might a psychological theory specify its own limits? And could you give a specific example?
Well, I think all psychological theories, or theories that deal with humans that have free will and free choice, are faced with this type of intrinsic limitation that I mentioned earlier, that there is no way in which, by some mathematical means, I could produce a prediction, say by analyzing your brain, of what your future behavior will be, that would be binding on your behavior if I were to show it to you. So if I keep it secret, you know, I can sort of chuckle to myself that you're doing exactly as I predicted. But if I were to show it to you, you can always choose to falsify it. And this turns out again actually to be another way of stating Girdles Theorem, that it's not possible for this prediction to be binding on you, that you can always choose to do something different.
I'd like to invite members of the audience, if we'll be taking questions from the audience in a couple of minutes, and if you would like to ask a question, there's a microphone here, a second one there, and a third microphone upstairs, and you're certainly invited. In just a minute, we'll be taking questions from the audience. Let me ask you, John, who are your heroes in science?
Gosh. Well, I mean, there are many different sorts of heroes, as it were. If you look back in history, people always seem to be gigantic in stature, people like Archimedes, and people obviously like Newton in the British tradition. And obviously, in the 20th century, there are obvious names like Einstein and Schrödinger and Heisenberg. But if one looks back in ancient times, every here and there you find someone almost anonymous who does something really rather extraordinary and amazing. In the summer, I was on the Isle of Samos, one of the Greek islands, for a conference, staying in the village of Pythagorean, which was named after Pythagoras. He spent his early life in this village. And on the outskirts of this village is one of the 7 ancient wonders of the world, which was built by an extraordinary engineer called Eupolinus. And it's known as the Tunnel of Eupolinus. And this is a tunnel about 1,000 meters long that runs from one side of the island to the other to bring water. And the puzzle always was for people for many hundreds of years of figuring out how this tunnel was built by 2 teams of people tunneling from 2 different directions through the mountain, working for 10 years, and then missing one another by just 1 or 2 meters. Whereas we know a few years ago in Mont Blanc, engineers from Japan managed to miss by 2 kilometers. And when one thinks about what the problem is, you know, you have to figure out how you know that you get to the right level on the other side of the mountain, and how you know what direction to go in. And by some rather simple geometry, just using triangles, you can deduce in exactly what direction you should head from both sides of the mountain. And this was really rather impressive use of very, very simple logic, just the property of a triangle having a hypotenuse moving in a particular direction. So everywhere you look, I think, in human experience, you find examples of a particular sort of genius for discovery and ingenuity. It's not unique to scientists or mathematicians.
It's interesting as I hear you reflect on what turn out to be relatively elegant, if simple, solutions to big problems. I come back to the same sort of sentiment that I had listening to your talk. It just seemed impossible. Isn't so much of the world that way? And it's just our limited thinking right now and the limits of our creativity that give us the illusion that things are impossible. All is possible.
Well, I would maintain that there's a lot of things like that. You know, there is a whole sector of things that seem to be impossible and undoubtedly turn out to be possible. And in fact, saying that such things are impossible is an important stimulus for people to actually try and go out and solve those problems. You know, they then have a special status. People want to shoot down that claim that they're impossible. But what one has discovered in science and mathematics in some of the examples that I've shown is that one can demonstrate, one can prove that a certain activity is impossible, that you cannot do something, that you cannot know something, that you cannot make something, that you cannot compute something. So it's not just a suspicion or a worry, it's actually a consequence of a particular theory or logical structure of very great generality.
Great. I think there's a question over here. I'd like to invite the first question, please.
Hi, thank you. Well, I only had one, but then you mentioned something about the world's fastest man, so I got to ask, who is it?
Oh, it was Frankie Frederick.
Who?
Frankie Frederick.
Okay. But my question is, assuming that you're right, that there are limits to everything, that we can't know everything, that there is a limit. My question is, once we reach that limit, whenever that is, 50 years, 500 years, whenever, then what?
Well, as I tried to show by my earlier example, you can have limits, but that doesn't necessarily mean that there's something that you reach. We can imagine different possible futures for science. So, for example, it's possible perhaps that the amount of information that's required to understand the universe is finite, or it may be infinite. Our own capability may be finite, but it may be unlimited. And there are various possible options. If our capability is finite, then it will be extremely fortunate if we just happen to reach the level of the finite understanding required to understand the universe. But if there's no limit to our understanding and the amount of information required to understand the universe is also finite, we would eventually overtake it. But I think one can see from some of the cosmological examples that what you're more likely to do is redefine what is the accessible information in the universe, and to see how close you can keep on getting to that. It is possible to have a curve which keeps on increasing, that is bounded above by some barrier. It keeps on increasing, but it never ever actually reaches the barrier. So in mathematics, something like the exponential function has this property. So just because there's a barrier which you're approaching, it doesn't mean that you never ever need reach it.
And I wanted to thank the question. That was real nice, right to the point. So that was a terrific question, and we'll come over here for our second one, please.
Actually, I wrote my question down on the card, but I'm really anxious for you to answer.
Please
so
do.
My name is Vili, so you can eliminate that card.
All right.
My question is specifically on the Mandelbrot set. It shows a great example of how infinite and finite works together. And if I visualize the Mandelbrot set, I can see somewhat of a center. My question actually leads to, if the universe kind of distributed itself in the Mandelbrot set way using that mathematical set, shouldn't there be a center? Shouldn't we visualize, aren't we capable of visualizing some type of center?
Well, there are two aspects to this question that I should say, for people who don't know what the Mandelbrot set is. This is a mathematical structure called a fractal. A fractal is something more general than the Mandelbrot set. It's really just where you take a pattern, it may just be a triangle, and then you repeat the pattern again on smaller and smaller and smaller scales in a never-ending way. And nature likes to do this. If you look at the head of broccoli or a cauliflower, you will see this type of design, that you have a certain pattern and then it's reproduced on a smaller scale still, and so on. And in principle, structures like this could keep on going to infinitesimally small scales. And people have wondered whether the universe is like this, so that if you kept probing the structure of space and elementary particles, whether you would keep on finding new structures on every smaller scale that you looked. At present, the standard picture of elementary particle physics is not like this, that it's believed that there is a bottom line below which there is no further structure. I mean, this may not be correct. There are problems with having never-ending structure on smaller and smaller scales, that you have to pay a price for it, that you have to have some energy which will support those structures, and this seems to be rather difficult to arrange. You require an enormous amount of energy to maintain this.
We'll take one more of the questions.